Hello, Assalamualaikum. My name is Muhammad Hazi Imran bin Hasnul Imran. So today, me and my other fellow teammate from Group 4 of Class EH2434A would like to present our task, which the title is Forming in the LNG Gas Plant in Gas Processing Industry. So before moving into the next part, I would like to give a short briefing of my teammates. First of all, I would like to introduce our responsible leader, who is Luqman Hazim. Next, our kindly assistant leader, Zairatul Azila. Moving on to the next part, the other fellow teammates, who is Aida Sharmin, Iman Nurul Aina, and last but not least, me, Muhammad Hazi Imran. So today I would like to give the introduction about the gas processing industry. First of all, natural gas is known as the cleanest burning fossil fuel extract from the ground. Transporting gas from the field directly to the base via long pipeline can be costly and impractical. Hence, natural gas is processed and liquefied into liquid for safer transportation process. Sour gas is a term that been used for the natural gas that usually contains hydrogen sulfide, which they usually weigh more than 5.7 milligrams per normal cubic meter. Other than high toxicity for humans, sour gas also contributes to corrosive effect on gas pipelines. As for the reason, sour gas need to be sweetened through adsorption of hydrogen sulfide in amine solution. Raw gas will pass through a series of the pipes and valve to separate heavier materials before proceeding with sweetening and liquefaction process. All these processes are done in gas processing plant. However, due to the forming as it occurs during the process, it have a significant impact onto the entire operation. This report and also research examine the key issue that caused by forming, and it determines the solution for preventing the issue.
Moving on to the heat transfer application, which is in gas processing plant, heat transfer mechanism is applied in the lean-rich amine process, where conduction and convection occur. Conduction can be defined as the transfer of heat energy from one particle to another by collision. On the other hand, convection means transfer of heat energy between a surface and adjacent of a moving fluid that moves from higher temperature region to lower temperature region. Sesmiati ETL 2019 stated that convection and conduction heat transfer occur in a boiler, which conduction takes place within heat exchanger itself and convection happens in fluid, which is the heat vapor and liquid substance. In the reboiler, liquid amine is heated, which releasing any gases as it's present, which is the sour gas, and the rich amines are converted to lean amines. During the heating process, molecules of amines collide with each other and causes the transfer of heat energy. Additionally, when the temperature of the environment increase, the temperature of the boiler will also increase. And when the temperature of the environment started to decrease, the temperature of the boiler will also decrease. When the heating process ends, lean amine are then pumped back into the absorption column to be used for sweetening process. Other than the boiler, which are related to convection of heat mechanism, the rich heat exchanger can also act as a heat conservation device. In the heat exchanger, heat is being conserved when hot lean solvent warms up the cooler rich solvents. This indicates that the lean rich heat exchanger use fluid, which the heat transfer that occurs due to the motion of the fluid. The convection of heat mechanism also occurs in both gases and liquids, which is stated by Byju's 2016.
The first problem caused by foaming in LNG or gas plant is the decrease of acid gas absorption efficiency. In general, as the operational temperature decreases, the efficacy of a main system to remove hydrogen sulfide rises, whereas the carbon dioxide removal occurs at a certain temperature. However, lower operational temperatures, in contrast, increase the likelihood that the liquid hydrocarbons may develop in the input stream, hence raising the risk of foaming in the system. Foaming will gradually reduce the extraction efficiency of acid gas as the surface tension of the aqueous solution decreases, causing poor gas-liquid contact, thus leading to the development of gas bubbles covered with thin layer of oil in alkyl amine or the amine solutions. The decreased surface tension is caused by the introduction of highly soluble hydrocarbons liquid in the amine contactor. Next, there are numerous approaches in the industry to prevent foaming in LNG or gas plant. One of the solutions is the determination of HCDP of the inlet gas as it might aid in the prevention of foaming. HCDP is known as the hydrocarbon dew point. It works by determining the temperature at which hydrocarbons begin to condense from their gaseous state as gas is cooled at constant temperature. HCDP can be utilized as it can prevent the intrusion of liquid hydrocarbons into the contactor. Hence, it also maximizes the extraction of acid gas while limiting the production of liquid hydrocarbons in the contactor by regulating the amines temperature and pressure. Although this approach aids in the prevention of foaming, it may provide inaccurate findings that are not significant for use in the control strategy of the foaming. Why? This is because the typical gas chromatograph can identify individual hydrocarbons up to N-pentane and aggregate the heavier components as a C6 plus value in natural gas applications. However, the foaming components are significantly heavier than C6, thus it is unsuitable to be used. Figure 1 shows the standard measurement ranges available for gas chromatograph. To prevent this, the C9 plus gas chromatograph may be used to enhance the control plan of foaming since it provides a more accurate estimation of HCDP and it also can analyze heavier components such as C6, C7 and also C8. Lastly, it can be inferred that for a better control of foaming strategy, it is better to utilize a suitable gas chromatograph such as C9 plus to prevent the development of foaming in the LNG or gas plant. Since the HCDP is under the operator's control, the operator must be alert if the HCDP reaches the stream temperature and reduce the HCDP before the liquid hydrocarbons start to form in the system and causes foaming. Other suggestion in reducing foaming development is by utilizing the carbon filtration. This is because it aids in the removal of hydrocarbons by constant filtering of the amine solution, thus reducing the contamination of the particulate.
I am going to present on the second major problem, which is amine degradation. Amine solution mainly used in sweetening process is known as alkanol amines. Despite alkanol amines' resilience to chemical breakdown, plant and laboratory findings suggest that, over time, alkanol amines may convert into undesired compounds from which the amines are difficult to recover. Irreversible side reaction of carbon dioxide, oxygen, and hydrogen sulfide occurs simultaneously with the absorption process, which result in solvent losses, corrosion of equipment, and generation of volatile degradation compound. Degradation products are known as contaminants, which could break down the base of amine solution and form different products. Solvents degradation initiates operational issues such as foaming, which in turn inhibit the gas sweetening process. In worst-case scenario, extreme amine losses may negatively affect the running cost of gas processing plant. Antifoams or defoamers usually used to prevent the formation of unwanted foams during the process. Before using in the amine system, any antifoam that is being considered should be evaluated. In most cases, a quick shake test is sufficient to rule out potential chemical of antifoams. The best defoamers in the market today are those based on silicone technology. This type of silicone has been proven to work better compared to organic defoamers. Silicone-based antifoams has lower surface tensions, which enables them to function in a wider range. This type of antifoams also proven to be more resistant to heat and chemicals. A few research has been done to identify the feasibility of antifoams to solve foaming problems in gas sweetening process. It turns out that silicon-based antifoams have been considered as a short-term measure rather than a long-term cure. The antifoam builds up in the amine solvent over time. Extra antifoam will be converted into adhesive polymer, blocking lean or rich amine in part because of this process. For a long-term solution, this option is not economically feasible to be applied. During the defoaming process, manufacturer guidelines of injecting the antifoams should be followed strictly. Overdosing antifoams causes reverse process of defoaming, in which it loses its ability to react with foamy solution. As a result, glycolic antifoam will accumulate in the cycle, which also led to oxygen reactions. Hence, this will eventually accelerate foaming process rather than reducing the existed problem. Rather than focusing on short-term approach, it is suggested to undergo a long-term measure by focusing on the mechanical approach. Installing a defoaming plate is one of the mechanical approach that can be done. Defoaming plates has an anticline located between the parallel plates that are too close to one another, which causes the gas to be released when frothy crude flows between the plates and heats them. This will increase the surface area, which causes the foam to move to fragment and collapse into the liquids. An effective technique for resolving operational issues and enhancing the performance of gas treatment system is routine sample collection and precise analysis of plant amine solution. Testing properly will yield to useful data regarding the physical and chemical state of amine solvent. To ensure they are obtaining the data required for the optimum control of plant operations, plants should re-evaluate their amine solution analysis program on a regular basis.
In this study, it can be inferred that gas processing industries are an integral part of the downstream operations that plays a vital role in transportation and production of either petroleum crude oil or natural gas. In the LNG or gas plant, processes such as absorption, stripping, gas sweetening and liquefaction involves heat transfer can be observed in this process, particularly at the reboiler and rich or lean amine exchanger, where conduction and convection are involved. However, difficulties may arise if these processes are not conducted effectively. Foaming, for instance, could disrupt the entire liquefied natural gas processing, which could result in a reduction in the amount of liquefied natural gas that can be generated at the LNG plant. A decline in acid gas absorption efficiency amine degradation are two of the key factors contributing to LNG or gas plant foaming in the gas processing industry. Foaming development process occurs during gas sweetening process. Hydrogen sulfide and carbon dioxide are two components involved in the gas sweetening process, and they must be effectively separated before being moved to another section of the amine system for the separation of much heavier components. However, due to the development of foaming caused by the intrusion of the hydrocarbons, the separation of the components is affected. Based on this study, the determination of hydrocarbon dew point and injection of antifoam might aid in the prevention of foaming. Other suggestions of solutions include the use of carbon filtration and defoaming plates. Thank you.